Okay, thank you for tuning in. You're really gonna want to see these notes played out. This will really help you down the line. So we're gonna talk today about angle measures and segment lengths. So we've spent some time talking about arcs and talking about central angles, inscribed angles, all those things. Now we're drawing it together and learning a few theorems that can help us solve for certain parts in a circle. So for a warm-up, what we're going to do in class is try and figure out what first angle 1 is and figure out the sum of those two arcs. And we're going to try and draw a relationship from them. So first things first, we have some labeling already done for us. And that looks like a triangle to me. So I bet you could guess why this is 80. Because those numbers better add up to 180 degrees, which makes this 82. Okay? So heck, that's one way we can find angle 1. Because look, now those are angle 1 and 80. They are supplementary angles, right? It's a fact that the measure of angle 1 plus 80 needs to be equal to 180 because it's a supplementary angle pair, linear pair. So the measure of angle 1 is going to be 100. And we're interested now about BC and AD as measures. So that'll be in degrees. But from what we learned in the last section on inscribed angles, we can see that this angle here opens up to arc AD. So and that's an inscribed angle, meaning that the angle's inside the circle and it has 3 points that form it that are all on the edge, A, B, and D here. So what that means is the angle is 1/2 of the arc, only for inscribed angles. So 70 is going to be 1/2 of the measure of AB as an arc, AD as an arc. So that one is 140. So that's a little bit of support why this is 140. And if we look at the other side, we have that 30-degree angle. I'm just going to sketch this real fast so you see it. That angle opens up to BC, and it's inscribed. So this is 60. Because it's the arc, or the angle is half the arc. So if the arc is 60, the angle is 30. So take a look at those notes if you need to see that from the last section. So what is they want to know the sum of the measures. So the measure of AD plus the measure of BC is 200, it looks like. So the big formula that we want to create from this is say, hey, 100 is half of 200. Is that a coincidence? The measure of angle 1 is 1/2 of the sum of these two angles. Might be a coincidence. It definitely could be. But in fact, it's not. So we have our first theorem that says, hey, if you want to find the measure of angle 1, no matter where that point is in the circle, it doesn't have to be in the center. The measure of angle 1 is the average of x and y. So the way I remember this one is 1/2 the front plus the back. It's also an average, if you want to think of it as an average. So for angle 1, it's over here. The front would be x and the back would be y. So that makes sense why the measure of angle 1 is 1/2 x plus y. I didn't give you a proof, but the warm-up kind of gives us some sort of idea with an example. All right. The next theorem that we're going to look at is this next one here. It applies in a bunch of different cases. You can see the 3 pictures drawn. No matter what you have, this is when the angle is on the outside of the circle. And it has 2 arcs that are intercepted by that angle, that massive angle that's going like this. There's 2 arcs. There's one here and there's one here. And that's true in all of these pictures. They've labeled them with X and Y. And we have a really nice theorem that we have the measure of angle 1 is 1/2 of X, which is the far arc, the far away arc, minus Y, which is the near arc. So really useful, and we'll do some examples with that here. But we have, so the angle 1 in the first one is 1/2 front plus back, and then if the angle is outside, and it aligns with one of these pictures, it's 1/2 far minus near. So let's apply this here. So I'll just use those formulas because the words help me a little bit. So this one, it's got that X in the middle. So X is 1/2 of the front plus the back. That first one. So all you gotta do is just go ahead and plug in. Okay, the front arc is 90, the back arc is 46. So X is gonna be 68. Yep. So that's an example of the first one. This next one's going to use the other formula. This is going to be 20 degrees is the angle, right? Equals 1/2 far minus near. So 20 degrees is 1/2 of far minus near, which is Z. Go ahead and multiply by 2 and move the Z over and move the 40 over. And that's the measure of this arc right here. So I knew to use this formula because I had an angle, it's not an exterior angle, and it's not an inscribed angle, but it's just an angle that's on the outside that comes in and intercepts the circle in 2 ways. So this formula, let's just plan a little bit. This one is going to be used for this picture, or this one is going to be used for this picture because it has the angle on the outside like that. Okay, so it's about an angle and 2 arcs is this category. When I say angle measures, it's an angle and 2 arcs. We got to fix this one though because 20 is not the angle. The angle on the outside here is 70 degrees. So from the vantage point of this, the far arc is W and the near arc is 110. So solving for W, we get that it's a 250 degree angle. And this is actually a special case because there's such a nice intersection here that it makes sense that this is 110 and this is 250 because that adds to equal 360 around the whole circle. But that didn't pan out here because we had 3 arcs. We had this, and this. We had 3 arcs happening here. So we couldn't observe that as nicely. But it obeys the formula. We can just use the formula. There's 3 different cases that they've shown here. We just use this one where it's 2 tangents. Okay. This one, same kind of deal. It looks like there's some interesting labels though, it's this one. That's the angle we choose. If you look at the picture, the angle is the one that's in the inside there. It's not a central angle and it's not an inscribed angle. It's kind of just like an angle in the circle. It's kind of random. That's what goes here. And the front is X and the back is 30. So I'll just go ahead and multiply by 2 again and get X. Okay. So, pretty nice formulas there. Not too complicated. You just need to know like what to do based on what's in the picture. So practicing these will help. Here's a cool example. It says a satellite in orbit above the Earth has a viewing angle of 17.5 degrees formed by 2 tangent lines to the Earth. What is the measure of the arc that can be viewed? So this is the viewable arc here. And we have not an exterior angle, but we have an angle on the outside there. So that angle is 1/2 the far minus the near. Okay, so I want to call this X. So near is going to be X. Now, what is the far? What is this? We have another special case here, right? Tangents hit at only one spot. So this circle is cut into 2 parts, green and red. And if red is X, and I know it's all 360, wouldn't the green be 360 minus X? Say X is 140, then the green should be 220 to add up to 360. So that is what we're going to plug in here for far. I'll multiply both sides by 2. Combine like terms. Subtract that over maybe, and move this over here. And we get, I think it was 162.5 degrees. So kind of an interesting question, and we had to come up with a label for that green, which was probably the most difficult part, but it's just the remainder from 360. You know, X takes up so much, and then green's just the leftover. Okay. So you may have seen this word thrown out a bit before, but a secant line is a line that intersects a circle at 2 points, and it goes through the circle. It's like a chord, but if you gave it ends and let it go on. So this is a chord, you know, something like this, but a secant goes through it. It's got arrows on the sides. Sometimes they draw the arrows, sometimes they don't. So this blue line down here, that's a secant. Whereas this blue line, that looks like a tangent. So secant and tangent are big in trig. You know, we use those a lot, but they're also huge in geometry. And then we have some chords over here, right? They stop at the endpoints in the circle. So that brings us to our last theorem, which is a little bit complicated, but there's actually a way to boil it down so we can use the same formula rather than all 3 of these. So let me read what the theorem says, and we're not going to prove it, but let's just read what it says. It says, from a given point, P, they're talking about P here. So P is right here, P is right here, P is right here. From that point and the edge of the circle, so the black, the product of the lengths of the 2 segments from the point to the circle is constant along any line through the point in the circle. So it's a very lofty type of statement, but what it's getting at, let me label some more points, and I'll try and do this on each problem for you. is they're saying that, hey, if you are at a point and you're a person standing right here and you're hanging out at P, what it says is that if you multiply the distance here to A, so that would be called PA, times the distance that you go to B, which would be the length PB, that equals if you went across the other segment and you multiplied them. So PC times PD. And we do have the tools to prove this. You know, it's a little complicated, but that's the idea. And they summarize it here with letters. They say, hey, just take A times B equals C times D, which is super nice. I recommend you use this because it applies to the other two cases. See how the formula changes down here? That's not so good, right? We want to try and use a formula that works every time. And that sentence up here written out, this is exactly what it's saying. So it gets a little bit confusing when the point is outside the circle, but as long as you just label A and B on one of them and C and D on the other, the formula is still the same. It's saying, hey, go from your point to an edge, to the edge it hits. That's PA. Go to the point, you know, it's always starting at P and going to the point on the circle. So PA and also the distance to the other point equals the distance here, PC, times the distance here. So you really have to put yourself at P, and you're standing here, and you're looking at the places where your lines hit the circle, and you're going out to each one of those. First, PA, and then you go PB, and then you go PC, and then you go PD. And if you multiply those together like that, it works out. So this is the same as this. Right? This would be PA, this would be PB, Y is PC, and this would be PD. Okay, so it's easiest to see with this one. You're at P, and you're looking out, there's going to be 4 or maybe 3 intersection points. And your job is to figure out how far it is to get there. So this is PA, this is PB. Right? And you're interested in where you hit the circle. That's what this theorem's trying to say, is there's a relationship between the distance to like where the line hits the circle and the point that you're at. And it's an interesting relationship, but it even works with this last one. So the theme is you can work with these equations like they are in the picture, but if we get used to labeling, we can use this formula every time. Okay, so this one's a little weird because we do only have 3 points. So those are both A and B at the same time, because like if we move the line a little bit down, we get 2 points, right? A and B, but it's almost like you just make it to the tipping point where they both agree. So the formula is still PA times PB equals PC times PD. All right, and I'm not trying to have you understand why this formula is true, because that's a lot of work to prove that. But I'm trying to just emphasize that we're going to use this way, and I want to show you how to do it. But it's really this formula that's the most useful. And if I had to draw a picture to go with it, I'd maybe pick one of the more general ones, which is these two guys. So this is P, this is A, B, C. Nope, you got to put A and B together. Okay, and you can move P wherever you want, but it's kind of got like these bungee cords tied to those 4 points. So you can move it out here, you can move P out here, but then those lines change a little bit. All right, let's just do the questions. So I'm going to draw my picture, call this P, call this my first line A and B, so it's line AB, and then I have the other one is CD. So the goal is to say, hey, if I go from point to A and point to B and multiply those together, that's equal to going from point to C times point to D. So this is going to be, the math is really easy for these. It's the setup that's confusing. So 6 times 8. I fell into a trap. What's PB? PB is this, which is 14. PC is 7, and PD is 7 plus Y. Okay, so we gotta solve for Y. So I like doing this part. The setup is hard, but I think it's much harder to memorize those 3 equations versus just using this one. You just gotta know how to label it, okay? You need to have a segment for AB and a segment for CD. Sometimes A and B will share the same point. So this is kind of like our special case. And when that happens, A and B are at the same spot. All right, I don't want to get too ahead of myself, but so this multiplies to 84. This is 49 plus 7y. This is 35, so y is 5. Okay. Let's do 3 first, and then I'll do 2, because 2 is kind of the weird one. So your intersection point is P, and then each line has a name. We're going to do A and B, and we'll do C and D. So A and B always go together, C and D always go together. That's important based on the formula I gave you. So PA times PB is PC times PD. You know, and each one of those is saying, hey, the distance between P and A, the distance between P and B, and so on. And then you just got to look at your picture and say, hey, it looks like PA is 3. It looks like PB is 7. They've got PC marked as M, kind of hard to see here, and PD marked as 6.5. So tidying this up, this is what we get, and 2 decimal places is cool. So that's what we get. Okay. Okay. So this is the, if you want to use these formulas, you can. This was the first one. This is case 1. This is case 2, and this is case 3, where you have a tangent. And when you have a tangent, it only hits at one point. So even though we want to have A and B on the first line, we have to settle with calling them the same thing. Okay, which would make sense. The tangent just has one point, so we got to call it the same thing. Whereas this line has a clear intersection here and a clear intersection here, and this is P. And what's really great is the same formula works, even if it's a different arrangement. So what we do is PB and PA are the same thing. PA equals PB. So they're both Z, and PC is 8, and PD is this entire distance, which is 24. Okay. So Z squared equals 192. And if we take the square root of both sides, I'm looking for approximates here. No need to reduce to simplest form, 13.9. Okay. Oh, look, here we have another. It's case 3. Now, these cases would matter if we were trying to use the formulas the textbook gave us. But with this formula, everything makes sense for every case, as long as you label it correctly, which is probably why the textbook doesn't use this formula, because it really relies on having like consistent labels. Like here, we don't have A, B, C, and D anymore. So you have a choice. I'm just gonna get rid of their labels, because at the end of the day, all I'm doing is solving for y. So those labels don't really matter. I want to replace them with labels that I know. We got the tangent, so we got the shared point, and we got C and D. This will help me just keep my mind straight. 10 times 10 is 7 times, it looks like, again, we have this distance is PD, which is going to be 7 plus y again. 100, 49, 7y, 51, 7y, and again, I'm going fast with these calculations. I just want to help you guys set these up. That's my whole goal. So y is 7.3. All right, a couple more. So PA, PB, PC, PD. Let's label. P is always the intersection. One of your secants is going to be AB, line AB. Your other secant is going to be line CD. That labeling is incredibly important if we want to use this formula consistently. Okay? PA is 14. PB is a long one. It's this, 34. PC is 16. And the distance from P to D is 16 plus X. I'm not asking about CD. I don't care about that. I care about where from the vantage point of P. That's what this theorem is about. It's all about where P is and your relationship to the 4 intersection points on the circle. So, I think in the key, I didn't even solve for X. I just left it like this for you guys to do. But I know you guys can do this, but I'll go ahead and do it out for you here for a second. I don't have the numbers handy. We got 476. 16 times 16 is 256. So now I got to do a little subtraction to move that over. And I have a feeling this is not going to go in nicely. Yeah, we get 13.75 or 13.8. Whoops. But yeah, that's the setup. And that's the answer. All right, the last one here, I wanted to give you another one of case 1 where P is inside the circle. So label the points where AB is a line and CD is a line. So don't go around the circle and label them. You gotta say, hey, this is my first segment that I want to pick. Call that AB. This is my second segment. That's CD. Or else the formula won't work. So it's very fragile. So PA is 9. PB is 8. PC is X. And PD is 2X. So this one comes out really nice because we have a perfect square. So X has to be 6. So this case is the easiest to see, I think, for the theorem. It's relating all 4 of these distances here from the point to its closest edge, its closest point on the edge of the circle. Okay, and this product is really remarkable, and it comes from similar triangles, which is something we'll talk more about in another chapter. Okay, so plenty of homework to practice. The good news is there's really only 3 formulas. We have the 2 at the top. We got front and back. We got far and near. And we have our very general product. This is called the intersecting chords theorem. At least this one is. So if you want to use these formulas, you can, as I've kept saying, but to me, I would never keep those straight. It's a little easier if we label points and do it